Good day, ladies and gentlemen. For the past 3 weeks, we have been discussing differentiation and its applications. Now we are shifting a little. We are coming to discuss integration. This is something you've met before, but the value addition we are going to do is that we are going to add two more important integration. That is the integration by parts and integration, using rational functions and know the applications in economics. So this is the section overview, and there's the outline, and the reading list is quite the same. First of all, let's look at a basic review. These things you've done at level 200. So integration is the opposite of differentiation. Very simple. So if you have the derivative of the function this, yielding this, which is equal to the derivative of df dx, then we have this function, right, which can be more or less retrieved by integrating what? The function that we have over here. What it means is that if we integrate this function, we will be able to get the function that we have over here. Let's look at very simple examples that you are familiar with. At level 200, you discuss many of these things. Two things are quite important in integration: indefinite integration and definite integration, right? When you talk about indefinite integration, what it means is that we talking about a situation where we have an indefinite producing a constant. So the solution is a system of functions, because once the constant change, your solution also change. We can have a very simple example here, right, where we need to integrate this function, and we have been given these values, right? We have been given these values, given the value of this and this, find a constant. So when we do our simple integration, we get this function, okay? So the constants we're talking about is here. So you have a system of curves, because as soon as C changes, you have a different function. But then we can more or less constrain ourselves by giving the boundary values and solving for C, and then we do have a specific, function. Definite integral, on the other hand, produces a figure, right? So when you are integrating the function within this limit, okay, what it implies is that you do the integration, you put in the values, and you get a specific figure. So if you look at this example where we are supposed to integrate within this limit, when we do the integration, we submit it, we get a simple, figure. So one thing you need to do, whenever you are doing a definite integral, it gives you a system of, functions which you have to use boundary conditions to specify it, or in the case of a definite integral, you get a specific function. The basic rules of integration also count, right? You have the substitution rule. You recall there are certain integrations which you have to make substitutions to be able to solve it. Elsewise, it's going to be extremely difficult. If you look at this integration, for example, it's a little difficult unless you make the substitution, okay? And then you find, dx, dy, you change the whole function. So if you make the substitution, that is u to be equal to this, then you have du to be equal to that. And then when you substitute into this function, you're able to reduce it to this integration, which you can easily sort of integrate. And once you've integrated that, you go back and put in the values, and then you have your original function. So integration by substitution is also there. The addition I'm going to make, as I told, is integration by parts and integration using, partial fractions. Now, you recall that there is this product rule in differentiation. When you have two functions multiplying, what you do is that you keep one, differentiate the other, plus you keep the other one. So this is called the differentiation using the product rule. From this formula here, we are able to reorganize this by integrating both sides, and then when we arrange them, we have integration of this nature. What it implies is that you may have an integration of this nature which you cannot. But then if you are able to break it down into what we have over here, this one, the integration is gone, but this one, it will boil down or reduce to an integration which you would be able to manage using substitution or using any other method. in certain literature, it's preferred to write this formula in this form once you make these substitutions. Now, let me look at it with specific examples, right? In this equation, we are supposed to integrate the function we have over here. This integration is going to be very difficult, right? If you don't try and reduce it to or use integration by parts. So we have this substitution, u is equal to that. When you take the differential, we get this. And our du is equal to what we have over here. Okay? Now from here, also when you allow this du to be equal to what we have over here, then what happens is that if we integrate both sides from here, we get this. And when we substitute all this into our formula, this is our formula. So we have u dv, which we have more or less standing here, which we have broken down into what we have over here and then what we have over here. So you see that it's equal to what we have over here, then can be reduced into the integration that we have standing here is quite easy to manipulate, right? This one is already there. And when we simplify it, we reduce it to this integration and then the constant, since it's an indefinite integral. So what happens is that it will be very difficult to do this integration, but with the help of integration by parts, we reduce it into this equation, which is quite easier to manage. There is another example here, and I would like you to take your time, right? Take your time and then go through all these examples that have been provided. At the end, there are some simple activities here. Please take these activities difficult. With integration, the bad part is that if you don't know the method to use to do that integration, you will spend the whole day on that integration and you will never be able to do it. And the good thing is that if you're able to do these simple ones, okay, once you know this integration, you know there's a formula, it becomes quite easier to do or undertake any integration. Now, the next integration that I would like us to discuss is a integration of rational functions where we use partial functions or partial fractions. Now, let's discuss what is a rational function. A rational function here, it's any polynomial that has got, expressed in terms of, denominator and numerator. So this is just a rational function, right? It has got a numerator, which is a polynomial, a denominator, which is a polynomial. There are basically two types of, rational function. We have a proper rational function, and then we have an improper rational function. Now, when the numerator, okay, the degree of the numerator is higher than the degree of the denominator, then we have a proper rational function. Okay, so this is a polynomial if the degree is 2, and this one is also a polynomial which the denominator if the degree is 3. The degree here is talking about the highest, the highest order, okay, or the highest degree. So this can be a quadratic, this can be, a polynomial raised to the power 3. Then we have a proper rational function. On the other way around, when the degree of the numerator is higher than the degree of the denominator, then we have an improper rational function. And I define the degree over here. Now, when you have a proper rational function, there are ways that you have to more or less, solve or integrate a function that is a proper rational function. Now, let's consider a rational function of the form that we have over here. And we are assuming that the degree of the denominator is greater than the degree of the numerator. So it means that we have a proper rational function here. And we will look at two examples, and then we will be able to understand it better. Look at this, rational function that we have over here. Okay? And we are able to, in this rational function here, we know that the denominator here, they are linear functions. So when you multiply, you get a quadratic. So more or less, the function is equal to, the denominator has got a degree of 2. Sorry, the denominator has got a degree of what? 2. All right. This can be, any function, but we assume for now that it's a constant. We can reduce this function into partial fractions and be able to integrate than leaving it as it is. An example will best illustrate the point. Look at this. Okay, this example. You will find it extremely difficult to integrate this function. Okay, we know there's a linear function, where they multiply, we get a quadratic function. There's a constant here, 4. But then, if we are able to reduce it into partial fractions, we would be able to easily integrate those partial fractions, right? So let's look at how we will reduce this, rational function, proper rational function, into partial fractions. What we do is that we write this function in this form, where these are a and b, and we are supposed to find this numerator a and the numerator b over here. Now, as usual, what do? They have a common denominator. So the common denominator is what we have over here. Now, 3 minus x goes into this, 3 minus x, okay, it goes into this, x plus 4 times. So we have x plus 4. The way we do addition of what? Fractions, the same thing. So when you come here, x plus 4 goes into this 3 minus x times. So you have b multiplied by 3 minus x. So we have this one, okay, and then we can expand. We have, x here. We have, there is no this thing here. And then we have also x here. What we do is that we equate the relatives. Okay? We equate the relative in the sense that when we take the x, a plus b is here, right? But there is no constant here. So it's equal to what? 0. When we take this one, right, this is a constant here. Sorry, when we took the x, a plus b was 0 here. There is no x squared here. Okay, there is no x squared here. So the coefficient of the x squared is 0, and that's why we have a 0 here. When we take this one, okay, this additive here, right, the coefficient here is 4, right? So we equate this 4 to what we have over here. We solve this one, right? 2 equations, 2 unknowns, this and this one. We solve it, and then we have a to be equal to that and b to be equal to that. So what it implies is that this our equation, this our proper, rational function. We can write it as a sum of 2 what? Rational functions, which can be simplified to what we have over here. Okay, we can also further go and simplify it this way. And from here, instead of more or less integrating this, we'll find it easy to integrate what we have over here. Right? The integration is what we have over here. And then, we integrate them being natural, giving us the natural log, a little manipulation over here. And then we have our natural log to be what we get over here. So the simple thing is that, we couldn't have integrated that function without reducing it to partial fractions. But with the help of partial fractions, we are able to, reduce this equation into partial fractions, and we are able to integrate them simply. Now, there are some examples here, right? I would like you to try your hands on them, and then we meet at the chat room. Now, let's look at another example. When the denominator of a proper rational function is a product of linear factors, some of which are repeated. An example is that this is a linear function, this is a linear function, but the linear function here has been repeated because there is a square here. You can see it clearly from here. There is a square here. Okay, let's look at a specific example, right? I have managed to make this one more or less a polynomial, a little complex. And then we have this function, this one is being repeated, okay? because of our title, some of which are repeated. In that way, this is how you express your rational function, your partial fractions. You express your partial fractions this way, and then using the usual method. So this one will go into this times. Okay, that's why we have a x plus 2 rho square. We use the same method. We expand it, and then you see for x square we have this coefficient. For x we have this coefficient, and then for the constant we have this coefficient. So we have to now equate the coefficients. So for x, the coefficient here is 2, but the coefficient here is what we have standing here. For x squared, the coefficient is 0 here, and then for the constant, the coefficient is 3. So when we equate that, we have these three equations. And when we solve these three equations, we get these equations over here. Now the next point is that we put them in here, introduce our sign here. Notice that if you expand all what is here, right, using simple fraction, if you expand all of it here, you are going to get the same equation here. And going further, you use your integrations, and then you integrate them, and you have something like this. Some examples here for you to try your hands on. And the last one, it's an improper fraction, right? And the long division. Notice that we have been discussing proper fractions, okay? When the degree of the numerator is lower than the degree of the denominator. Here we have improper fractions where the degree of the numerator is higher than the degree of the denominator. So how do you deal with issues of this nature? I will look at it from a specific example, and I think it will make it much clearer. Assuming you have this integration to resolve, it's going to be very difficult. But the good thing is that the degree of the denominator is 2 here. The degree of the denominator is 3 here. That is why it makes this one an improper fraction. But then we can reduce it to a form that will make it easier for us to integrate. You recall long division, okay? So we have the x plus 2 over here, and then we have all this long thing over here. So we start x plus, x goes into x, 2x raised to the power 3 how many times? It goes in this times. We multiply this by this, we get this. We multiply this one again by this, we get this. You know, we have a line here, we subtract from what we have over here, and then we get this. And then we come again, x goes into this how many times? This times. We multiply this by this, we get this. We multiply this by this, we get this. Again, we subtract again, we get this. And then we go the last round, and then we have this as a constant. So if we want to simplify this equation that we had over here, this is what we got, and is what we have standing here. We can reduce it into what we have standing here, right? So what we have standing here, it means that when we multiply, it means that when we multiply this one by this one and add it to this, we are going to get this whole equation. Again, when we multiply this, denominator by this, and then we add this, we are going to get the whole equation over here. So what happens is that the whole integration, which we have reduced to this one, we can write it in this form. So this form, integration has got is additive. So we can now, separate the two, right? We have this additive, and then we have this additive, and we'll find it very easy to integrate this one using logs, and we have our results. So the first part over here, when we integrate, we get this one. The second part gives us this one, and then we have our results. There are also some examples here which you may have to work on, and we will meet at the chat room if you do have problems. Now, some applications of, what you have to know is that, the applications of integration are quite vast. Whenever we have a marginal function, we can establish a total function from a marginal function. That is one major application of, and I have an example here, okay? A very nice example here where we are trying to establish a total, a profit function from both the cost function and the revenue function. You can take your time, go through this example and convince yourself that, this application is quite real. There is also an example here where you are trying to more or less establish, you have been given a marginal propensity, right, to save, and then you are supposed to more or less establish the savings function. And I have the solution is simply provided here, and there's an activity for you which you have to, spend some time and work on them yourselves. And then if there is anything, let's meet at the chat room and discuss. There is also one nice, example activity here. You may like it. And there is also an activity which involves partial fraction. Here too, you may have to use your prowess in partial fractions to resolve or, reduce this one to partial fractions and solve them. And here, one thing is that you have already been given partial fractions, and then you try to solve this problem. One thing I need to tell you is that the application of integration is varied, very, very, very varied. So it is left to you to look at the question, be able to write the reduce the problem into a mathematical problem and use the method of integration to solve it. I think this brings us to our discussion this week. Thank you very much, and let's meet at the chat room. Bye.